2 people from the Dawn mission here at JPL, and then 2 from the Messenger mission at the Applied Physics Lab. I'm going to introduce everyone. We've got Tim Weise, the Dawn Deputy Mission Manager, who leads Dawn's mission flight team, which operates the spacecraft throughout the entire mission, from launch through cruise to asteroid operations. He started on the project 2 years before launch. His team received the 2014 trophy for current achievement from the Smithsonian National Air and Space Museum. Very well deserved. And he recently taught a spacecraft design class at Cal Poly San Luis Obispo. Wouldn't that be fun? And with Tim is Kristina Larson, who currently works as a system engineer for the Dawn mission. Kristina's tasks include building, reviewing, and testing sequences, commanding the spacecraft, investigating anomalies, and building tools. She also recently spent time working on the Mars Exploration Rover Opportunity as a tactical downlink lead. She's been a member of the Dawn team since 2008, beginning as an intern while still studying at USC. And at the Applied Physics Lab, we'll be hearing from Jim McAdams, who's the mission design lead engineer for the Messenger spacecraft. Apparently he likes being the first. Messenger's the first to orbit Mercury. He was on Galileo, the first to orbit Jupiter, and on the NEAR mission, which was a Discovery Program mission, the first to orbit an asteroid. So he's into those firsts, and he's got some great missions. Jim leads the team that designed Messenger's very complicated trajectory, which included a flyby of Earth, 2 flybys of Venus, and then 3 flybys of Mercury before going into orbit around Mercury in 2011 and staying in orbit for 3 years longer than originally planned. Quite a feat. And then we'll have Andy Callaway, who has more than 18 years experience in space mission operations and ground system development efforts. He began his career supporting a variety of commercial and international geosynchronous communications satellite launches and operations. He spent 6 years supporting the Tropical Rainfall Measuring Mission, and he's been a member of the Messenger operations team since he joined APL in 2002, and he's been their mission operations manager since 2007. So I will turn it over to Tim and Kristina.
Hello, so I'm Kristina, and so we're members of the team for the Dawn spacecraft, which was part of a low-cost class of missions, part of the Discovery program. Oops, wrong remote. Here we go. Okay, so our mission is, we're propelled by ion propulsion, which really makes our mission unique. Ion propulsion is 10 times as efficient as standard chemical propulsion. We have actually traveled 3.1 billion miles to reach Ceres, and this has only been possible through the use of ion propulsion. Our ion propulsion system uses xenon fuel. We ionize the atoms, and it's definitely a more gentle type of propulsion, but it's been extremely efficient and powerful, and that's what enabled us to get to Vesta and Ceres. So since we separated from our launch vehicle, Dawn has spent 44,890 hours thrusting. That's over 5 years just of thrusting in space. And this is very different from missions that use standard chemical propulsions. You're usually limited to shorter propulsive maneuvers, and Dawn's default state really is thrusting. We've spent 69% of our time in space thrusting. Since we left Vesta, we've spent 93% of that time just thrusting to get to Ceres, and we've only missed one period of 95 hours of planned thrusting. Let's see. Since we were removed from our launch vehicle, the ion propulsion system has delivered 10.6 kilometers per second, which is 23,800 miles per hour difference in velocity. This is cumulative, so we've thrusted in different directions. When we were approaching Ceres, we had to slow down relative to Ceres to match Ceres orbit. But cumulatively, our system has imparted 10.6 kilometers per second, and this is 2.5 times the previous record holder. And this is actually more than the difference in velocity given by a launch vehicle to send something to the International Space Station. And just to give you an idea, for example, for a Delta II heavy rocket, the main engine alone, when it's fueled, weighs over 100 tons. And we've cumulatively been able to deliver more Delta V than what that can deliver. So it's a very efficient system. Our ion propulsion system, we only expend about 1/4 pound of xenon per day. And at the highest thrust level, our system delivers a thrust that's comparable to a piece of paper on your hand. And we're not even near using the maximum thrust level right now. So it's really amazing that such a gentle thrust has enabled us to travel so far to Ceres right now. At our current thrust level, it would take us about 11 days to go from 0 to 60 miles per hour, just to give you an idea. Right now, I'm going to show a video. It's the ion propulsion video, and this will give you an idea of how the system works.
This is Mike Meacham at the Jet Propulsion Laboratory, and this is an episode of Crazy Engineering. Here at JPL, we have to solve problems that nobody's ever solved before, and sometimes the solutions can seem a little crazy. Today we're going to talk about this bad boy, an ion thruster. What's so special about an ion thruster? What makes it different, and how does it help us get through the solar system? Let's go talk to an expert. All right, guys, we found our expert. This is Mark Raymond.
Hi, Mike.
Mark, where are we?
We're at a vacuum chamber here at JPL where we test ion engines like this one, and we have 3 just like it on the Dawn spacecraft that's out in the main asteroid belt between Mars and Jupiter.
Can you explain what makes an ion thruster different than other types of thrusters?
Sure. Well, first, let's remind ourselves how a regular rocket engine works. You take a gas and you heat it up, or you put it under pressure, and you push it out of the rocket nozzle, and the action of the gas going out of the nozzle causes a reaction that pushes the spacecraft in the other direction. With ion engines, instead of heating the gas up or putting it under pressure, we give the gas xenon a little electric charge, and then they're called ions, and we use a big voltage to accelerate the xenon ions through this metal grid, and we shoot them out of the engine at up to 90,000 miles per hour. And they're going out so fast that each individual ion gives a relatively large push back on the spacecraft.
So if I'm the spacecraft, could you push me as hard as I'm going to feel from one of these thrusters?
I can try.
Okay, I'm ready. I can take it. I barely felt that.
That's right. The engine pushes on the spacecraft as hard as this single piece of paper pushes on my hand. In the zero-gravity, frictionless environment of space, though, gradually the effect of this thrust builds up. At full throttle, it would take Dawn 4 days to accelerate from 0 to 60 miles per hour.
Wow, that is a slow car, isn't it?
It is, but instead of thrusting for 4 days, if we thrust for a week or a year, or as Dawn already has for almost 5 years, you can build up fantastically high velocity. It's what I like to call acceleration with patience.
Why is that a good thing? What's the trade-off? What can Dawn do that other spacecraft cannot do?
The ion engine gives us the maneuverability to go into orbit, and after we've been there for a while, then to leave orbit and go on to another destination and do the same thing. In 57 years of space exploration, Dawn is the first mission targeted to orbit any 2 extraterrestrial destinations. It wouldn't be possible without ion propulsion. For 2 centuries, this had just been a little smudge of light against the stars. Dawn got to spend 14 months at Vesta and turned it into a whole new, complex, fascinating alien world.
Mark, where are we right now?
This is the Dawn Mission Control Room at JPL. This is where we control the spacecraft from. We tell the spacecraft where to point the thruster, what throttle level to use, and that's how we guide the spacecraft through the solar system.
And we're on to the next location, which is Ceres.
That's right, a dwarf planet, in fact, the first one ever discovered. We're going to get into orbit very soon, and the pictures are going to be coming into this very room.
Very cool. Stay tuned for those photos, and stay tuned for some more crazy engineering.
It's going to be cool.
Pretty crazy. So using our ion propulsion, we actually achieved a really big milestone yesterday morning. Our spacecraft was captured by Ceres gravity, and we officially began orbiting Ceres. So now we are officially the first spacecraft to orbit 2 extraterrestrial bodies, and we're the first spacecraft to orbit a dwarf planet. So it's really exciting. We're really excited. So our IPS engines, they're powered by our ginormous solar arrays. Our solar arrays are about 65 feet tip to tip. And just to give you an idea, that's about, they could stretch from the pitcher's mound to home plate on a professional baseball field. So they are large. And when Dawn was launched, it was at the time the largest interplanetary spacecraft launched by NASA. These solar arrays, when we first launched, they provided about 10 kilowatts of power at Earth. And now that we're at Ceres, they provide about 1,300 watts. So when this mission was being designed, it was definitely a big challenge to account for the large differences in solar distance that we would be covering, and to have a large enough array to provide enough power once we were at these very large distances from the sun. We also didn't have a lot of data before launch on the performance of solar cells at these long distances from the sun. So along the way, we've done many calibrations of our solar arrays, of the solar cells, to give us better ideas to work into our power models so that we could design our thrusting trajectories. And at the maximum throttle level with our IPS system, when we were close to Earth, we could only use 3,000 watts out of the possible 10,000 watts. So that kind of gives you an idea of how much we had to overcompensate so that we could have enough power once we were at Ceres. And just to put it into perspective again, we have about 1,300 watts right now at Ceres provided by our solar array, and that's 1,300 watt light bulbs. So we're not really working with a bunch of power, and so it's definitely a challenge to make everything work within our budget. And I'll show one more video right now just to show you all the science that we were able to accomplish at Vesta using these 2 systems. You could go to the video. Let's see. Do Dawn's farewell portrait. Pretty cool, right? Yeah, so amazing images, detailed images like this is what you can expect from our time at Ceres. So we're really excited to see what we see there. And just to give you a couple facts about Vesta, on the South Pole, as you saw, there's a huge crater, the Rhea Silvia crater, and it's more than 300 miles in diameter deep. And at the center, it's the second tallest mountain known in the solar system. It's more than twice the height of Mount Everest. So pretty cool. And I will hand it over to Tim.
All right, thank you. How much time do we have left? Okay. Right. Exactly. We'll go quick. So in terms of challenges that we've experienced since launch, one of the big ones was that we had 2 reaction wheels fail since launch. We had one failed before Vesta in 2010 and another one right after Vesta in 2012. And what the reaction wheels do is they're basically spinning masses that we torque them around to make the spacecraft turn where we need it to turn. You kind of think of a bicycle wheel. If you take a bicycle wheel and you spin it really fast and then try to move it, it turns the other way, or if you slam on the brakes, you go over the handlebars, that kind of thing. That's how we use reaction wheels. So when the first one failed in 2010, we immediately switched over to using the reaction control system, which uses little jets that are pulsed that do the same thing. They just push the spacecraft around the direction we need it to orient, to point our antennas at Earth or point into the thrust direction. And so originally we weren't planning on operating in that mode, and so that uses more fuel than we were expecting. And so we immediately started on a new flight software update to be able to use 2 reaction wheels with RCS controlling the third axis, because you need 3 wheels to be able to control the spacecraft in 3 dimensions. And so that was our first big challenge. We used reaction control system all the way to Vesta, then we switched to using the wheels because that's better control for doing the science. We accomplished all of the Vesta mission, and then as we were departing, the second wheel failed. And again, we switched right back to RCS control and undertook a big effort where the whole team brainstormed to figure out, okay, how are we going to do this mission with only 2 wheels? And the whole team pitched in. We had many brainstorming sessions. We figured out how to adjust the flight software some more to save fuel to make it operate more efficiently. We normally, before Vesta, we would, while we were thrusting with the ion system for so many years, every week we would stop, turn the high gain antenna to Earth to return all of the engineering data so we could study the health of the system and make sure it was stable. But each one of those turns costs fuel with hydrazine. Because you fire the jets, you don't get it back. With reaction wheels, you turn, and then they just use electricity, so you don't use as any fuel to do the turns. And so one of the ideas we had was to say, well, why are we stopping once a week? I mean, that's 7 days. I mean, everybody's used to 7 days in a week, so that was, seemed kind of arbitrary. So we said, how about 2 weeks? How about 3 weeks? And we ended up with 4 weeks. So, and all of our crews to Ceres, we would thrust for 4 weeks at a time, then we'd stop, turn the high gain antenna back to Earth, and return all of the data to review and see how the spacecraft would perform. And we'd check in with the low gain antenna twice a week just to make sure it was still proceeding and there was no anomalies or that sort of thing. And one of the really, in terms of that change, one of the biggest challenges was to have the team feel comfortable that they were seeing the spacecraft often enough. You kind of you have this comfort zone of getting your data once a week and reviewing it and making sure it's healthy, and then switching over to this other mode where we only had a small snippet into the spacecraft to say, okay, it's still thrusting, and these 100 channels are working right, just for that time slot. And so it was a big challenge to convince ourselves that was a safe way to operate. And obviously, it turned out to be a good solution because now we have this wonderful mission ahead of us at Ceres with plenty of fuel. We have margin to complete all of our science objectives at Ceres and then have some fuel left over. So that was a huge effort, and is really testament to the great thinking by the team. Yeah, there's a question.
Similar to a gyroscope?
Yes, basically a gyroscope. It's more of a heavy, massive object in a spinning mass, and as you torque it faster or slower, the resulting torque on the spacecraft results in the motion of the spacecraft. And then the other big event that I want to tell you about was in September. We had an anomaly. I don't know how many people were following at that point, where one of our regular check-ins, twice a week, Thursday morning, the spacecraft was in safe mode, and took us a while to figure it out because it was actually a combination of two different faults. That it was initially in one type of safe mode, and we couldn't quite lock on the signal, and then we bargained with the DSN to get more antenna time, and by lunchtime we figured out that it had gone from the first safe mode to the second safe mode. And that resulted in losing 95 hours of thrusting, like Kristina mentioned, which also impacted our trajectory, because as we're approaching Ceres, we're trying to slow down to match Ceres' orbit around the sun, and by not thrusting for those 95 hours, we weren't going to slow down in time. So we ended up redesigning the trajectory where we go past Ceres, and you get captured by gravity over there on the top of the picture, and then come back in and get into our final orbit. And so that was a huge challenge for the navigation team, because none of our analysis covered this case. I mean, we knew if we missed thrusting, things were going to change, but we didn't know by quite how much. And so by this resulting trajectory, you can see all of the approach was coming from the left side of the screen is the sunny side of Ceres. And so all of the optical navigation images that we planned were all coming in from the lit side. As soon as we went to the dark side, we couldn't get navigation images anymore. And so we have about 5 or 6 weeks without the optical data to be able to refine our orbit understanding to complete the maneuvers all the way into Ceres. As you've heard yesterday, we successfully captured, and we have about 5 or 6 weeks more of maneuvering to get into that final, or our first science orbit of RC3. So again, I mean, it was a huge challenge. In terms of human factors, we went from thinking everything was fine Thursday morning to splitting the team to work 2 shifts through a weekend and be ready to uplink our next planned sequence on Monday evening. And by being able to do that, we already had a planned sequence to go for the next month. And we were able to restore the spacecraft to its correct state and then just run that sequence. And while that one was running, figure out the rest of the changes and the impact to the trajectory. And so that was a quick turnaround and great human factors adjustment of going to working the night shift, and you thought you had a weekend, and and then let's see. So actually, if you could show the last movie I was going to show, and then we can turn it over to the next step. This is the Ceres trajectory. So this basically gives you a better view of the orientation of the spacecraft as it's approaching Ceres. Now we're on the far side of Ceres in this view. We're looking towards the sun. You can see Ceres in the middle of the screen there. And you can see, so the spacecraft's coming towards us. And you'll see as it gets a little bit bigger, the thrust beam is pointing towards us. That means we're slowing down relative to Ceres. We're pushing the spacecraft in the other direction. And now we slow down a little bit more, and then by now we're already captured into orbit. So if we had stopped thrusting, we'd be in an orbit around Ceres, just not one that we would use for science collection. You can see the spacecraft there reorienting the beam so that we can actually get into our RC3 orbit. RC stands for rotational characterization, and it's the third one we do where we image the body for a full revolution of the body so we can make a spin movie and see how it looks. Since we're running out of time, there's other images of Ceres that you guys can look at on the JPL or the Dawn website that have all the latest animations of the really cool pictures that we've gotten so far.
Okay, thank you very much, Kristina and Tim. Dawn is an amazing spacecraft.